We now review some logic that we will need for understanding proofs of linear algebra. This is a very brief review, but there will be other notes posted, and also there will be significantly more exercises that you have to solve in order to review. First, the definition of a proposition that we usually use is a declarative sentence or declarative statement. It must be either true or false. It cannot be both at the same time. For example, the following statements are declarative sentences, which means propositions. The number 2 is a rational number. This is a true statement. We can write this as a quotient of two integers, which is the definition of a rational number. For example, we can write 2 as 4 over 2, or we can also write it as 2 over 1. Another statement or proposition is a number square root of 2 is a rational number. This is a false statement. Square root of 2 is not a rational number, it's an irrational number. And to show that this is false, it requires a proof that we will not cover. Usually this is covered in number theory. Example for things that are not statements, sentences that are not statements, something that's not a declaration. So for example, run, that's an exclamation. How are you? That's a question. It's a sentence, but not a declarative sentence, it's a question sentence. Or even the statement that Brussels sprouts taste good, that sounds like a declaration. The problem with this is that it depends on who says. So if 2 or 3 people get together, there can be an argument whether or not this is a true statement. And in mathematics, at least at this simple level, we're not supposed to have disagreements about what is true or what is false. We're supposed to have some kind of proof for that. And it shouldn't depend on the person whether something is true or false. Combining propositions using operators. We have the conjunction, which means we use AND to combine together two propositions, A and B. We use this so-called wedge symbol in between them as a notation for an AND operator. Disjunction, A or B, we use this so-called V operator or V sign, A or B. And then a negation, not A, and the symbol is sometimes this simple single wave, and sometimes this special notation for the negation is what's used. Then we also have the implication. A implies B is how we read this. And we also say many times that if A, then B. It turns out that the truth table of this is equivalent to not A or B. So you should be familiar with how to create truth tables to figure out the value of a proposition, a complex proposition. If we have two propositions A and B, then we have to write down all the different combinations, whether one is true or false. So we have altogether 4 possibilities: true, 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 false, false, true, false, false. And then the A implies B is only false when A is true and F is false. But for example, if A is false, then it doesn't matter whether B is true or false. In both cases, the implication will be considered true. If you compare this truth table with the truth table of not A or B, then you will see that they have the same exact values, and that's what equivalence means, that they are either true or false at the same time. Now we also use the equivalence of two propositions, either used with this triple equal sign or this double arrow. A is equivalent to B. Statement A or proposition A is equivalent to proposition B. And this equivalence really means two implications. It's equivalent to saying that A implies B and also B implies A. A very useful tool is to know the laws of negation. How do you negate complex logic expressions? For AND and OR, you have to know that the negation switches them around. So the negation of A and B is not A or not B. And the negation of A or B is not A and not B. The implications negation is easiest to figure out using this equivalent form, that A implies B is equivalent to not A or B. So if you negate that, not A or B, then using the previous laws, we take the negation inside and we switch OR to AND, and we negate both of these. So we get that the double negation is just cancel out, and we get A and not B. This is very useful for proofs. Next topic is quantifiers. First, the universal quantifier for all. This is the notation, it's upside down A. For all x, the statement P of x is true. So here the proposition has this variable x in it. For example, if we want to say that the square of a real number is also a real number, you should know that this is a true statement. And another way to write this using the universal quantifier, well, we say that a real number, what we really mean is that all real numbers. So a better way to write this, to see the universal quantifier, is to write that for all real number, its square is also a real number. And then to write this down with just symbols, for all x real number, x squared is a real number, because x squared is in the set of real numbers. There are different ways to write these symbols down. Another way to write is using, instead of space and comma, another way is to use parentheses to combine together statements. So this one, it says for all x real number, x squared is a real number. Of course, there are different notations in different areas of math, and also it's kind of part of philosophy on this basic logic. And for other notation, it's interesting to see the Principia Mathematica by Whitehead and Russell. This is from page 379, where after several hundred pages, they prove that 1 plus 1 equals 2. And these are some funny notations. So in some cases, you might realize that there is this existence notation. Of course, this was created in the beginning of the 20th century, more than 100 years ago. So the typesetting was also a problem in those times. The other important quantifier is the existential quantifier. It says there exists. This is backward E, capital E. There exists x such that P of x is true. An example is to say that there exists a real number such that 3 times the number minus the number 5 is equal to 4. To write this down with a compact notation, there exists x real numbers such that 3x minus 5 equals 4. Or using this parenthesis, there exists x real number, and then the proposition that 3x minus 5 equals 4 with the variable inside. For existential statements with the existential quantifier, if you want to show that it is true statement, that something exists, then usually we have to find it. Which means in this case, for example, that you have to calculate x by solving the equation for x. In some cases, it's impossible to calculate things, so then there are some special ways to show that existential statement is true, but in most cases, we actually calculate the x that exists. In fact, in some cases, there might be several x's. So there exists A really means that there exists at least one. So if there are more than one, that's also fine. That makes the statement also true. These quantifiers can be also combined together, if we have, for example, two variables x and y, for all real number x, there exists a real number y such that y is less than x. That's two quantifiers combined together. For all real number x, there exists a real number y such that y is less than x. In fact, if we are working on the universe of real numbers, like what we do most of the time in most undergraduate classes, except the complex variables class, if we know that we will be working with real numbers only, then we don't necessarily have to write this notation, that real numbers notation, out. We could just say that for all x there is a y such that y is less than x. And what happens sometimes that at the beginning of a section or chapter we state that we will be working with real numbers. Or sometimes it even happens that at the beginning of the book this is stated once and then it's not written out anymore. Now the proof for this, so for an arbitrary x we will find a y. And this y should be less than x, so one way to get a number less than x is that we subtract from x1. And we choose this for y, and we know that x minus 1 is less than x. Well, what we have in this case is that this y that we find, for each x, we find a different y. So actually y changes with x, which is fine. The order is also important for quantifiers. If you change them around, many times the truthfulness of the statement will change. For example, if we say that there exists a real number y such that for all real number x we have y is less than x, writing it this way, we have that there exists y real number such that for all x real number y is less than x. This is a false statement. So this states that there is a real number which is smaller than all real numbers. But of course, there is no smallest real number. So you can think of this that way. But actually, it's also useful to use negation to show that something is false by showing that the negation is true. To negate a quantifier or quantifiers, what we have to do is switch them and then negate the statement inside. So if you have two quantifiers with two variables, that means that the statement's supposed to be a function of two variables somehow, p of x, y. So it's a proposition with two variables x and y. And if you want to negate for all x there is a y such that p of xy, we switch the quantifier for all to exist and the exist to for all. We keep the order of x and y, and then we negate the statement. So it's not p. For example, if we negate this previous statement, that it's not true that there is this y real number and that's for all x real number, y is less than x. We take the negation, we switch the quantifier, so now it says that for all y real number, there is an x real number such that it's not true that y is less than x, and we negate inequality by switching around the inequalities and allowing equality. So what we get is that for all y, there is an x such that y is greater than or equal to x. Or saying it differently, such that x is less than or equal to y. So if we show that this is true, that means we are showing that the negation of this original statement is true, and that makes the original statement false. And we show that this is true, this last statement, by finding an x for all y, such that x is less than or equal to y. And again, what we can do is we can choose x equals y minus 1, which is less than or equal to y definitely. And for each y, we can find this x. Another example for these quantifiers, the question is whether it's true or false. We are working with real numbers. This is an implication. The proposition is that if x is less than 3, then x squared is less than 9. In some cases, graphs are very important tools to show what the statement is and to show that we want to prove something. So in this case, x squared is a quadratic function. To find a place where x squared is less than 9, it's easy. From the graph, what we see is that it's between -3 and 3. And that means that we can find an x less than 3, for which this is not true, that the square is less than 9. For example, -4 shows that the statement is not true. And then sometimes you get an idea that something, how to show something, but it's another question, how do you write this down? So I think in this special case, I think I would accept this as a proof that x equals -4 shows that the statement is not true. By the way, that means this is called a counterexample. Where something shows that for all statement is not true. Actually, if you want to use quantifiers and rigorous notation for the proof, then the statement that if x less than 3, then x squared less than 9, what it means is really that what we mean here is that for all x, that's supposed to be 3, x less than 3 implies x squared less than 9. And the reason we get a counterexample is because when we show that it is false, we can show it by showing that the negation is true. And the negation of this for all statement can be written as there exists an x such that it's not true that x is less than 3 implies x squared less than 9. And then the implication can be written as not x less than 3 or x squared less than 9. And this is what we have to negate. And when we use the double negation, they cancel each other. And or changes into and we have to negate this second inequality. And the negation of x squared less than 9 is that x squared is greater than or equal to 9. And now, by saying that x equals -4, if we choose this number, it's true that this x, -4, is less than 3, and the square 16, the square of -4, is greater than or equal to 9. That means we have shown that this last statement is true, which means the negation of the original statement is true, and that means the original statement is false. So in this case, we show that the negation, which is the existential statement, is true. That means that we find a counterexample. So this is a brief review of logic. Again, there will be more review material posted online, and you have to solve more similar homework assignments.